Hello everyone, welcome back to Bevy Basics. I hope you all had a wonderful Thanksgiving. In episode 4, we're going to be talking about ordering systems. We're going to cover schedules, flush points, and system sets. More specifically, we're going to talk about adding systems to schedules, and then we're going to do a deep dive into schedules and talk about what they are. We're going to talk about explicit system ordering APIs such as before and after. We're going to cover implicit flush points that happen between schedules. We're going to talk about applied deferred and how we can use it in your game. And finally, we're going to cover defining and configuring system sets. First up, let's go over a very quick review of the Add Systems API. As you've seen with the Add Systems method, you can directly assign systems to specific schedules like startup, update, fixed update, and post update. For example, you can add systems to the update schedule by simply writing .add systems and then the schedule name. But what are schedules? Let's dive in, starting with the main schedule. We haven't talked about this yet, but we've used other subschedules that are in the main schedule. Main functions as a kind of meta schedule. However, fundamentally, it is still just a schedule, similar to any other you might use in Bevy. Its primary role is to organize and execute a sequence of other schedules, which are identified by their labels. The main schedule contains an exclusive system that iterates over its list of schedule labels and executes them using world.runSchedule. As such, the main schedule determines the order of the other built-in schedules that run as part of the main game loop. So what systems are in main? Just the one exclusive system. So how do we use main? Generally, we don't. While it's possible to add systems to main directly, in practice, this is not encouraged. Instead, developers should use the subschedules provided by Bevy. For example, update when adding systems. The schedule, like we've seen before, determines when the systems run. The best way to just understand how these schedules work is looking at the documentation for the main schedule. You can see that it basically describes the order that everything runs, as well as giving details about what runs every frame and what just runs once at startup. So let's quickly cover this. By default, main is going to run the following schedules in the given order. On the first run, it's going to run pre-startup, startup, and post-startup. Then, on every frame during the main game loop, it will run first, pre-update, state transition, run fixed update loop, update, post-update, and last. These are essentially the built-in schedules that Bevy provides. Additionally, you can add your own schedules, but that's usually something that we'll reserve for more advanced use cases, and you don't need to worry about that for now, and we're not going to cover that in this video. In general, it's recommended that you use the startup, post-startup, fixed update, and update schedules. You don't want to order your systems by putting them in different parts of the built-in main schedule. That is, I do not recommend that you add something to first in order to run it before update. Instead, you should order your systems using the explicit system ordering APIs and system sets, which we'll get into next. Quick aside, so you understand fixed update. Fixed update contains systems which only run after a fixed period of time has elapsed, as opposed to update that simply run every frame, regardless of how long that frame took. This is useful for very specific use cases, such as physics, where you want the updates to be consistent. Or rather, you want the delta time between updates to be consistent, such that mathematical calculations do not return strange errors when frames become very long or very short. So now that we have a basic idea of schedules, let's talk about how you, as a user, can order your systems. The most basic way to do this is by using the before and after APIs. By default, systems within a schedule run in parallel, without any predetermined ordering. The before and after methods are used to establish dependencies between systems. When you specify that a system should run before another system, you're ensuring that it completes its execution prior to the start of the specified system. Using .after guarantees that a system will only run after the completion of the system it is dependent on. For example, imagine if you want a shield system to trigger when a player's health drops below a certain threshold. This way, it can protect itself from further damage. Without any ordering, you might have a damage system and a shield system. Each frame, those can run in any order. Thus, on 2 consecutive frames, you could have the damage system run at the end of one frame and then the beginning of the next frame, essentially running twice in a row. In that case, shields would not have a chance to run before the damage was applied the second time. If the player experienced this, they would be likely very frustrated. They would expect their health to drop and then the shield to kick in, but it didn't. So what do we need to do as a developer to ensure that behavior happened? Add systems to update using the same add system API, but when we add the system, say .before apply damage system to whatever shield system we had. Thus, we would see the shields and the spaceship would never take damage 2 frames in a row without the shield system having a chance to run. The chain method allows ordering multiple systems in a chain. It is essentially syntactic sugar, or a more straightforward way of writing system ordering without repeating many before and afters when you have a long chain of systems that you want to order. When you use the chain on a tuple of systems, it ensures that the systems are executed sequentially in the order they are defined in that tuple. Just by using those 3 APIs, before, after, and chain, you can very easily specify your dependencies between systems and accomplish much of what you need to when thinking about systems and the dependencies of those systems. But there's a couple more key pieces of Bevy that make things slightly more tricky. As we talked about before, there are certain things in Bevy that are not executed immediately, such as commands. In episode 1, we said those commands would be executed by Bevy by default in another system that had exclusive world access. That is true, but when does that system run? And how can you use that knowledge to choose when you should order your systems if they depend on commands being applied? That's when we get to flush points. Flush points are moments in the execution of your game loop where Bevy applies all pending change, such as entity creation, component insertion, or despawning entities. Essentially, the commands are being flushed and then they're being applied to the world in the order they were sent to the queue. So if you have one command and then another command, they'll both sit in the queue, and then once Bevy hits the flush point, they'll be applied to the world in the order they were added to the queue. So what does this look like, and when are they applied? By default, the flush points happen between each schedule. That means that after first runs, we'll have a flush point. After pre-update runs, we'll have a flush point, and so on. The most important one for us, then, is after update. If we add all our systems to update, that means that on one frame, during update, our systems will run, then a flush will happen, then the next frame will happen, and all our systems will run again. So on the same frame, any systems, whether they run before or after each other, will not see the commands applied to the world. So if you insert a component to an entity, and then another system runs after it, that system will not yet see that entity added to the world. It's important to note that this is the current logic as of Bevy 0.12. I want to mention there's current efforts to try to make this less confusing for new users, since this is a very common foot gun. In the future, flush points may be applied automatically when you order your systems using before and after. Let's look at an example to understand why system order of execution with regards to flush points is critical to understand. Without being separated by a flush point, there's a risk that a system might despawn an entity before another system tries to insert a component to that same entity. In this example, let's look at multiple frames with regards to the order of execution of multiple systems in the update schedule. Remember, by default, in update, we will not have flush points. Thus, multiple systems that run in a row will queue commands to the world. Then, once the flush point occurs, all those commands will be applied in order. On frame 2, despawn faraway entities runs before add shield. If, in our current game, the spaceship happened to go far off the screen such that despawn faraway entities despawned it, and at the same time, a shield was triggered for that spaceship, then the order of the commands would be the despawn and then the insert component, and we would get a panic. Although in the future, Bevy might handle this automatically, there could be other game logic bugs that don't actually add panics that could come with misunderstanding the flush points and how they're applied in your systems. So it's very important to understand what a flush point is, when a flush point happens, and how it affects your systems. If you're encouraged to add all your game logic to update for normal systems that run every frame, then how can you handle flush points without using multiple schedules for every time you want 2 different systems to have a flush point in between them? This is when applied deferred comes into handy. While implicit flush points occur automatically between schedules, you might sometimes need additional flush points within a schedule to ensure consistency in your game state by adding the apply deferred system. For example, in the despawn entity add shield component example, we could chain together 3 systems using the same explicit system ordering APIs, but including the applied deferred built-in system. We could have add shield component, applied deferred, and then despawn entity all chained together, such that there is a flush point after the entity is despawned, and that the shield query will never fetch an entity that doesn't exist in the world. Great, so now we understand explicit system ordering and flush points, and how to add our own flush points using applied deferred. But unfortunately, scheduling is a very hard problem, especially as our apps scale. You'll have multiple dependencies where systems from one plugin will need to run after systems from another plugin. You won't really want to import all kinds of different systems from various plugins and use these APIs to order things. Occasionally you will, but I suggest that you use the explicit system ordering APIs mostly to order systems within a plugin. For example, we might order the different systems in the movement plugin, like update velocity and update position, to run in a specific order. However, what if we want to orchestrate systems across multiple different plugins such that they run in an order? This is when SystemSets come into hand. SystemSets are a fundamental tool for organizing and ordering systems. They allow you to group systems into sets and define their order relative to each other. This provides a more scalable way to approach ordering systems when you want to have logical groupings of systems across multiple files. So what is a system set? A system set is simply a label that can be applied and group systems together. System sets become functional when configured for a specific schedule. They are configured using the configure sets method on the Bevy app. More specifically, we usually define a system set as an enum where each variant represents a grouping of systems. These are usually in logical order, especially when dealing with system ordering. System sets are also a powerful tool that can be used for applying things like run condition, but this episode will focus just on their ability to order systems together. In order to make an enum a system set, you just derive the system set macro. Then you'll configure that for a specific schedule. For example, you could say that in update, my set should run in order using the chain method, such that first, then second, then third run. Then you will use the .inset API to add systems to that system set. Note that the chain API here is the very same API that we use to order systems. We can order system sets in the very same way that we can order systems, using the before, after, and chain APIs. With those features at your disposal, you can leverage the power of Bevy to run code in parallel, but also run it in a specific order when needed. Although parallelism gives us a lot of power and efficiency, it also comes at a cost of more complexity. Tools like before, after, chain, and system sets allow us to manage this complexity as our application scales. To really solidify all that we've learned, let's see how these different ordering constraints can be applied to the game example that we've been building in the previous videos. As always, I recommend you follow along during the code example. You can find the complete source code on GitHub. Simply clone the repository to your local machine. Then, with cargo run -p episode 3, you'll be able to run the previous episode, make your modifications there, and then you can double check your answers against the episode 4 folder. It's time to take a look at a practical hands-on example. I prepared today's example ahead of time such that we can go through the code changes and visualize them as a diff. I think this is the best way to visualize how scheduling and ordering logic can be applied across our app. I encourage you to follow along and add these changes to your own working copy. To start, let's look at main. The only change we will make to main is adding a single schedule plugin. This plugin is where we will configure our system sets and manage flush points. So let's take a look. In schedule.rs, we have 3 main things. First thing, our enum definition of in-game set, which derives system set. For each of the variants of the enum, we will use that variant to group together systems with similar behavior. The 4 variants are user input, entity updates, collision detection, and despawn entities. Second, we've configured the in-game system set with the update schedule. This defines an ordering for the enum variants relative to each other. First, despawn entities will run, then user input, entity updates, and finally collision detection. The last thing we've done is added a manual flush point between despawn entities and user input. This way, any systems that despawn entities can be added to the despawn entities system set. After that set, all the commands that despawn entities will be flushed and the changes will be applied to the world. Then, the next three sets, user input, entity updates, and collision detections, will see those changes reflected when they query the world. In other words, we won't get any stale data. That is, queries won't return the entities that were just despawned. Let's move on and look at how we've updated our existing plugins to use the new system set, starting with movement. In movement, we have two changes. First, we've chained together the update velocity and update position systems so that they run in a consistent order, frame to frame. Before, we might have updated the velocity twice in a row without updating the movement. This means we might have missed user input for one frame. This is something the user would likely not notice in practice, but logically there is still a dependency there, so it's worth adding ordering to these systems. Second, we've added both of these systems to the entity updates set. Since these entities are being updated, that is, we're changing the components for the entities in the game. Next, debug. Debug has one simple change. The print position system will run after entity updates. This way, it runs consistently after the update position system each frame. In this case, we could have simply imported the update position system directly. But as we discussed in the slides, I recommend using SystemSets to order systems across plugins. Let's move on and look at despawn. The change here is simple. We've added the despawn faraway entities system to run in the despawn entities set. Since all this system is doing is despawning entities, this is the logical set to use for this system. As we saw before, this means that after the system runs, there will be a flush point. Next, we're going to look at the spaceship, asteroids, and collision detection. We've made some more substantial changes here. Let's start by taking a look at spaceship. In spaceship, we've introduced a new system, spaceship shield controls, which we'll take a look at in a bit. We've chained together the three systems so that they run in order. This is because we'd like any logic for spawning, for example, firing missiles, to take into account the movement of the ship. This way, the missile will be spawned at the correct location. In terms of ordering these systems relative to other systems, we've chosen to add them to the user input set, since all of these systems process the user's input and do something as a response to that input. However, it is important to note that this decision is somewhat arbitrary. There is no single right way to order all systems across our app. For the spaceship controls, some of these systems also do other things, like updating the spaceship velocity and spawning missiles. In essence, deciding on which set systems belong to is more of an art than a science. There is no right decision, and as your app grows, you'll need to adjust your schedules and system sets to make sense with your new behavior. In a future episode, we'll learn how to decouple the input handling from the missile spawning and velocity/transform updates that we are applying in the various control systems using events. This would allow for better boundaries and make the choice of which variant of the in-game set to choose much more clear. Now let's look at the rest of the changes to the spaceship file. We've updated all of the single and single mute APIs to use the non-panicking variants that return a result. This way, if the spaceship is ever despawned, our application will not panic. Instead, the system will do an early return and not run any of the spaceship logic. Finally, the new system, Spaceship Shield Controls, will simply insert a spaceship shield component when the user presses Tab. After we finish reviewing the rest of the code changes, we'll see how, without system ordering and proper understanding of flush points, this insertion could cause a panic if run on the same frame as the spaceship is despawned. Before we do that, let's move on to asteroids and see the changes. We've added the spawn asteroids and rotate asteroids to the entity update set. Again, this decision slightly goes against the definition of our sets, since spawn asteroids is spawning an entity, not updating an entity. I want to emphasize that the sets that I've chosen here are nothing more than a starting point for grouping the app game logic. As your application scales, you will need to be able to make judgments about how to best order your systems. There's flaws with the decisions that we've made here. When it comes to ordering your systems, it's a difficult problem. To improve this, you could choose to have a separate set for spawn entities. But again, this would not be a perfect solution since you're adding more sets and more complexity. Note that in this case, we're not chaining the systems together because spawning the asteroids and rotating the asteroids are not dependent on each other. In addition to the set changes, we've also removed asteroid-specific collision logic. The reason is that we'd like to also support despawning the spaceship, and as such, we've made the logic more generally applicable across multiple component types. We've removed the handle collision system from our asteroid plugin entirely, and we'll see soon how we've added a new generic system to collision detection that will be able to handle both spaceship and asteroid collisions. So let's take a look. We've updated the original collision detection system to run in the collision detection set, which, as you may remember from before, runs after entity updates. We've also added 2 new systems for handling collisions. First will handle collisions for asteroids, and the second will handle collisions for the spaceship. The old system, Handle Asteroid Collisions, is now generic and can take any component type T. Yes, that's right. Bevy supports generic systems, allowing you to write code once, but still have it work across multiple components. Let's take a look at what that looks like. Here, the exact same code for handling collisions is defined. We haven't changed a single line of the function body. The only difference is that with asteroid has been replaced with T. The generic type T has one trait bound. It must implement the component trait. This way, we can add the handle collision system for any type that derives component, and the entities with that component will despawn on collision with any other entity that does not have the same component, T. This means that asteroids won't despawn when they collide with asteroids, just like before. Let's go back and go through the example I mentioned earlier, where adding the spaceship's shield could cause a panic. Right now it can't because of our system ordering, but what if we didn't have the ordering? Let's make sure we understand where that panic would occur. Looking at the schedule.rs file, let's remove the flush point. Then, we'll run the game and move towards an asteroid while holding down tab. This will cause the spaceship to be despawned. But since there is no flush point, the shield system will still think the spaceship entity exists in the world and try to insert the shield component. Then, when the commands are flushed after the update schedule, a panic is going to occur. And as you can see here on the screen, the panic is stating that we tried to insert a component after we despawned that entity. And that concludes today's hands-on example. In my opinion, scheduling, system ordering, and flush points are some of the most nuanced and confusing pieces of working with Bevy. That said, scheduling is also something that is very critical to understand. Unlike other slightly more advanced features like run conditions or events, scheduling and system ordering is not something that you can opt into. You need to understand it. As your app scales, you are going to have systems that have dependencies, and you need to be able to order those systems appropriately. Thus, I highly encourage you to make sure you understand the concepts that we've covered in this video before moving on. In future videos, we'll move on and cover more of Bevy's features. We'll look at events, local resources, state, and change detection. As always, please leave any feedback you have in the comments. For those of you who have been using Bevy for a while and have built significant applications with it, I'd like to hear from you. How do you handle schedules and system ordering in your applications? And with that, thank you all for watching, and I hope to see you all in the next video.